streaming and recording. Okay, let me go ahead and post the link. Let's see. All right. So today what I wanted to do was something I kind of talked about briefly last time, which was the idea of I want to talk about a little bit about what type inference is and how type inference works in the context of a graphical data flow language. So I guess specifically the main things I want to talk about tonight are, so first of all, just as like a counterexample, I want to talk a little bit about how the G compiler for LabVIEW works and what it does, which is not type inference. It's called type propagation. And I'll see a couple of examples of how that works, and then we'll go into like the basics of what type inference is, and then after that go into like the specifics of how it works in rebar, or like the basics, and then go a little bit into how rebar deviates from like the normal paradigm of type inference to do things like auto borrowing and other kinds of coercions. So that was my main plan, and I think I'm going to try to keep this to about an hour tonight, because going for 2 hours last time was definitely way too long. And hopefully if this turns out well enough, then I'll keep like the video of this and like keep it as a reference for like anytime someone wants me to explain how type inference works. So yeah, and definitely if you're listening, like at any time, ask me if you have any questions, and I will try my best to answer them. So okay, so the first thing I want to look at is, so what does G do, and like how is it different from type inference, and how are they similar? So what type inference is for is to solve a problem that a lot of statically compiled compilers have, which is they need to be able to associate a type with every expression in the program. And in a text-based language, what that means is like, you have like a grammar for your language that might include like expressions that kind of look like this. You have like, you have variables, and you have constants, and you have binary expressions, and you have variable bindings and assignment and function calls and arguments and so on and so forth. And the grammar defines like how this gets turned into like a tree of expressions. And the goal of the compiler, at least when the language is statically typed, is to be able to come up with a type for every one of those expressions. And there's several reasons for this. The main one is you generally need to be able to assign a type to expressions to determine whether your program is well formed. You also typically, later in the compile process, once you've validated it, you will need those types in order to do efficient code generation, which is one of the main points of having a statically typed language in the first place. And then also in interactive environments like Visual Studio and the LabVIEW IDE, having that type information around is useful to be able to reflect back to the user in some kind of user visible form, like whether that's IntelliSense giving you the little tooltips on variables in Visual Studio, or whether it's like something like the wire colors or the context help in LabVIEW that tells you like, hey, this is the specific type of this thing. So those are like some of the main reasons why your compilers need to be able to solve this problem. And so the way that some older language compilers, I'm thinking of like older style C, languages that don't have any notion of type inference, but that do require static type declarations. The way they'll typically do this is, they'll start with like leaf level expressions that they know that you can, easily figure out a type for. Like if you're a constant, we know your type. If you're a variable that's already been declared, then we know your type. And then they look at, composite expressions that are built up out of these things, and they, from the leaf level up, they kind of build up like what the type of each expression is from the parts and from the structure of those expressions. And that's typically why you need things like a variable to be declared before it gets used, so that you can have the notion of the type of a variable before that variable, in any of the places where that variable appears and where its type is going to get used. And the G compiler for LabVIEW does something kind of along those lines. Graphical languages have kind of like a built-in like structural advantage in that the things that we're computing types for are basically just the wires. Like our expressions and the values that are the results of our expressions are pretty much just captured by the wire. So like if we know what the types of all of our wires are, then we've basically done our job. Well, and related to that, like if we know the types of all of the terminals on our nodes that are connected to our wires, I mean that's basically the same thing. So what the LabVIEW compiler will do is it will basically for each node say, okay, let me get the types of my inputs, and then I'm, based on whatever node it is, I'm going to do some computation and then figure out what the types of my output should be, and then send those down the line to all the nodes that are downstream of me. So effectively, it's like we're executing Dataflow, but like in type land, or where all of our values are types. We're taking inputs, transforming them, and sending them down to outputs in the Dataflow order of our program. So for instance, we have a program here where like if we have an array constant, an array of string constant, this type is array of string, it passes that down to to index array, which takes in the array of string input and figures that out, that this output needs to then be string because that's the element type of the array. It passes it down to string subset, which then says, okay, that's the type that I need. Now, this so this is called type propagation, and it gets a little bit more complicated in some areas of syntax. Like for instance, if you have a loop with a shift register that has multiple history values, something like, let's see if I can do this. Yeah. So if you have like a shift register that has 3 history values, what this will cause us to do is to run type propagation over the entire body of the loop once for each one of those history values, because each one of those could potentially cause changes in the downstream, in the types that are downstream of it. But by and large, like that's the main complication. Like by and large, it's basically just input types go to output types according to the rule that's defined by whatever it is that the node is supposed to do. And typically, like this is pretty powerful, because anything you can express in terms of like the programming language that the compiler is written in is a valid behavior for for the type propagation of a node. Anytime you can write a program that says, given these inputs, I will produce some outputs, like that can be a reasonable implementation of the type propagation of the type prop for a node. And the main thing you need to do when adding a new node to the language is just define how its types propagate, and then also how to generate code for it. But like that's the main thing you need to do in order for it to be able to like semantically analyze and so on. So that being said, there are some limitations to this approach. And the main limitation is that you need all of your for a given node, you need all the information about its types to come from its inputs, or else be specified, some other way. So a good example of that is obtain Q. So obtain Q is ultimately going to produce, a Q of some inner type, that we can pass to something like enqueue. And so but there's this input on it, which is element data type. And we need to supply a value for that. We need to supply a value for that, because otherwise the node doesn't know what kind of queue it's going to create. It doesn't generally look, down the wire at the things that are using it. And I'm kind of previewing what type inference would do, but there's really no other way for it to know, unless you tell it what kind of thing you want to go into this queue. There's no other way for it to know what kind of queue to create. But the thing is, this is what's known as a type-only terminal on a node in LabVIEW. This value, this actual string value, is going to go nowhere. It's not going into the queue. Its only purpose is to tell the queue, or the obtain queue node, this is the type of the thing that you should create. And there are other nodes like index array. If I just have index array, wired to string subset, obviously there are problems, because this is missing some required inputs. But without those inputs, it can't even tell what the it can't really tell what the type of this output should be. What it does is it defaults to saying it's double, because it defaults to saying that the input is array of double. But then that conflicts with string subset, even though there's a solution here, which is that the only possible way this can work is if this output string and this input is array of string. But it's not really going to figure that out unless you explicitly give it an input of array of string. So yeah, by and large, that is how it works. That there is, in order for a node to know what its outputs are, it has to get that information either from its inputs or from some other means, like some other configuration on the node. There's one counterexample to that I know of, and I'm going to go over that real quick, and it's called the variant to data node. And the point of this node is to take in a variant value, which can be essentially anything, as a pointer to basically any kind of data. And then it also takes in this type-only input, and to basically tell you what type the output should be. And then it tries to turn the inner value in the variant into one of those types of data, or otherwise it fails and creates a default value. But so if you wire an integer to that type input, then okay, now the data out is turned to integer. But if you just wire the output to something that expects a string, well, this node is actually going to look one step down the wire and say, oh, I'm wired to something that expects a string, so I'm just going to change myself to be a string. And now this, basically the type on this wire is fine. It still needs an input, but it's okay with saying that this is going to be a string. But this is kind of dependent on some internal state of the compiler. And the way you can tell that is that, so here I have a variant to data wired to insert to array. So this terminal defaults to double because there is no input array, so now this wire is double. Well, if I connect this array of string input to the array terminal, now all of a sudden this wire breaks because it still thinks that the input, it still thinks that this wire is double, even though now the downstream input is expecting a string. But if you do something that causes it to recompile, like deleting this wire, then it fixes itself and says, oh, this thing must now be a wire of string type. And this is essentially because all the variant to data node can do is look at this downstream, the thing it's connected to downstream at the moment that, at one single instant compile, and get whatever type it happens to be set to at that time. If that terminal gets changed later because of other things that happen during type propagation, well, it's just going to be broken because it doesn't really have the ability to say like what should this downstream thing be really. It just looks at okay, what does it happen to be at any given moment in time. So, and that is the only counterexample I know of, and it kind of goes to show you that even though that's what it does, for a node to do anything with its outputs and determining its types doesn't really work all that well in general. So I'm just going to kind of leave that without any further comment. So Rebar a while back had a part of its compiler that essentially worked the same way. It did type propagation, by propagating types down wires in Dataflow order. And there was a specific point where I realized that this was not going to work for what I wanted to do with the language. And the specific point I realized that was when I wanted to create the option, the constructors for the option type, including the none. So an option is a generic type, option of t, which where a value can either be sum of t or none, and it kind of represents like the concept of nullability. So with none, you're constructing a value that is of this option type, but you're not taking any inputs to do it. You're just outputting a value that is option of t for some t. Well, what that means is you are essentially forced, because you have no inputs, you are essentially forced to get the specific information about what type that output is some other way. You either need to be able to get it from your output, or you need something else, something that essentially amounts to a type annotation on your node. And because I didn't want to go the route of type annotations, at least not where necessary, I decided that type inference was going to be the way to do that. Because we can't do the thing that variant to data does, where it looks at whatever immediately downstream thing it happens to be connected to and what its type happens to be at that moment. Like, that doesn't generally work. Instead, what you need is a more robust way of saying, like, this thing and the things that use it downstream all need to somehow share a type, and they need to collectively figure out what that type should be together in order to come up with a type that is valid for all of them. Okay, so that's kind of a segue into, so what is type inference? So type inference is a different way of solving this question of, like, how do we get types for all of our expressions? And at a high level, what it is you're going to come up with, you're going to assign type variables, variables whose values are types, to each of the things in your program, each of the expressions or nodes and wires, anything that can have a type. And then you're going to use constraint solving to come up with the best match, the best type match for all of those types, based on how all of those type variables relate to each other and how they get used. So, like, going back to our really simple, like, generic expression-based text language here, we can sort of guess that, like, in this first example, so we have expressions like y plus 2, and x, and we need types for all of those. So we can start by giving each one of them type variables, which we'll just name after t and a number. So, like, we can say y is t0, 2 is t1, which we can already say is integer. And then y plus 2 is going to be t2. X is going to be t3. And then, okay, so then we can say, well, so what we do after that is this process of what's called unification, where we figure out based on the structure of the program, which pairs of type variables need to be the same type, and we merge them together in such a way that they essentially become the same variable. We figure out how we can make them the same variable. So the first place where we would do that is for y plus 2. So the plus expression is something that takes two values of the same type and adds them together to get a value of still the same type. So it's like t and t makes a t. So we know that that means that the two sides of this expression need to be the same type. So we're going to unify them together. And then once we've unified them together, we know that that's going to be the same type as the result type, or the type of the overall expression. So we'll then unify those together. So that means that we're going to unify t0 with t1, and then we're going to unify the result of that with t2. So if we do that, so we have one variable that's just like a bare unbound variable that has no known value, and then another one which is already bound to int. If we unify those together, well, the most we know about them now is that they must both be int. So to do that, we just kind of say, okay, let's get rid of t0 and make both of these things t1, which is int. And then again, we're gonna unify t1 with t2. And again, this is an unbound variable with something that whose type we already know. So t2 is just going to get overwritten with t1, so int. And then we have an assignment statement, and here again the rule is pretty simple. We're going to say that the type of the thing on the right is going to become the type of the thing on the left. So that means we unify t1 with t3, so x is now t1, which is int. So that's a fairly simple example because we only had like a few type variables and one type that they could all be, but it shows you this like structural process of like figuring out which things must be connected to each other and then merging them together. So a slightly more complicated example would be if we have like a call to a function, and then we're assigning the result of that call back to some other variable. So here the expressions are, there's an expression for each one of these arguments. There's an overall expression for the call, and then there's an expression for the thing that we're, for the assignment back to the variable. So we're going to set up our type variables kind of the same way as before. So bar is going to be t2, naz is going to be t3. And then foo of bar baz, we're going to say that foo is going to be like the name of a function that has some type that's it's going to be a type that takes two parameters of some types and returns another type. And then the overall type of this is going to be the return type of our function, so that's just going to be t6. Yeah. So what we've got to do now is figure out which things are connected to each other. Well, we know that our arguments have to be compatible with whatever the types of this this function are. So that means that we're going to have to unify t2 and t4 and t3 with t5. And we also know that the assignment is going to take the right side of that expression and carry it over to the left side. So that means that we're going to have to unify t1 with t6. And what this would actually look like is would depend on what those actual types were. And I'm not really going to make them an example, but like those are basically the constraints we would have to solve, was like setting each of these pairs equal to each other to come up with a value for what the final expression R is. So those are some simple examples. And if you read like a textbook like Types in Programming Languages or something that talks about type inference, it'll describe coming up with all these inference rules for a language, which are essentially like logical statements for each of the kind of expressions in a language that relate, hey, if I know that this expression is something, then I know that these parts of it must be these other types, or vice versa. And the rules that it comes up with will generally be like bidirectional. So you can either figure out, like using the same rule, you can either figure out the type of a whole from the types of its parts, or the type of the parts from the whole. It should work the same, either way. But that's geared more towards like a formal description of like how you want to do type inference for your particular language. But switching back to graphical data flow, again, we have this advantage of like simplicity in the fact that the only things that we really need to unify or to compute the types of are the types of our wires and the types of the terminals that they're connected to. And in fact, we kind of know that like the only places that we're really going to need to do unification are of like the source type of a wire with its downstream sinks, because those are going to be the same variable, so they're all going to have the same type. So our type inference algorithm essentially is going to be, we walk over all of our nodes and construct type variables for them in basically a set of type variables, which is really a set of bindings of names to expressions representing types that we can manipulate, things that are either type variables or references to literal types, or composite structures of like structure types or variant types or class types or so on. And then once we've got that, we've set up that initial set of variables with like some initial structure based on what we know about what each of these nodes take in and pass out. Then the main thing we have to do is just unify the type variables at the upstream of a node with the type variables at the upstream of a wire with the type variables at the downstream of the wire, and we're basically done in theory. So here, for instance, we can say, so if we change this a little bit around and we say we're going to have a none value, but then we're going to assign that over with a sum of 0. So the way this might work in the compiler is, the first we might say, okay, the 0 constant, its output terminal has a type variable with integer type, and then the sum has one type variable for its input, and then another type variable that's like option of that input type for its output. And then similarly, the none is going to have an option of yet another type variable for its output. And then the assign is going to have its own type variable, but it's going to use the same type variable for both the input for both inputs. Actually, what it's going to have is the top input is going to be a mutable reference to that type, and then the bottom input is just going to be that type. So that's all of our type variables. That's like 4 or 5 or 6. And then we can just walk over these wires in Dataflow order and say, okay, this one has to get merged with that one. This one has to get merged with that one, and this one has to get merged with that one. And at the end, what we come up with is that this wire, which before we didn't know the type of, now we know it has to be option I32 because it has to be compatible with this other type, which is also option I32. So we've taken, a node that has no inputs and is solely dependent for its information on its output, and by the context of how that output value gets used, we're we're able to determine its type. To show you another kind of similar example, there's a node called create vector, and now that type inference is in place, this is able to create, so what this creates is an empty vector of type vector of t. So it's a vector with 0 elements and it's generic in the element type. So here we have the same similar kind of error that says if it's unwired, then the type of this value has not been fully determined. If we then take that and wire it into an append to vector and make it mutable, so append to vector is going to take a mutable reference to a vector and add something on to the end. Well, here again we've said with just this information we're able to say that this is now a vector of I32 because it gets used in a context where we require a mutable reference to a vector of I32 in order for it to compile. So that's the only type that it can be. So we don't need any other information for this, just to say I'm going to create an empty vector of I32. That's all it needs. So I'll give you one other example of this, slightly more complicated. So here's the field accessor. So the field accessor takes in a reference to a struct, and it has some number of selected fields, and it's going to output references to those fields in the struct for each one. So what this has to do is initially, when we're first creating type variables for this, we don't know specifically what kind of struct we're going to take in. All we know is that this thing coming in must be some kind of struct, and because we have these field accesses, we know that it has to have a field named 0 and a field named 1. We don't know what types those are going to be either. So we create individual type variables for these outputs, and then we group those type variables together into sort of a composite expression that means a struct-like type that has types with at these field names at fields 0 and 1. So then if we actually connect a real struct type to this, well, now this type coming downstream says I'm an actual struct type and I have fields 0 and 1 and they're both integers. So we can unify that real struct type with this struct-like type variable and say, oh, well, if your 0 type is integer, then I'm going to unify that with my 0 field type. And if your 1 field type is also integer, I'm going to unify that with my 1 field type. And so now these have, all of these have proper types on them because the only things these can be are the field types of whatever came in here. Okay, so that's that's the basic general idea of how things work. And within the rebar compiler, there are a few different kinds of things that can be values of type variables. There's literal types, there's simple type variables, there are struct invariants. And then there are reference types, which are a little bit special. And then also the type variables can be constrained by one or more traits, basically saying I'm any type that satisfies all of these traits. However, there's another feature of rebar that complicates type inference a little bit, and it's the best way to illustrate it is with what's called auto borrowing. So the snippet up here at the top is, so we're using the create copy node. So we're taking in a string value by reference, and we're going to create a deep copy of it and pass the copy of it out to the output node. What the compiler does is, so the important thing is this node is taking the input by reference. But this input is not actually a reference. It's just, a string. It owns a string. So what the compiler is going to do is it's going to rewrite this internally to this bottom snippet where it puts a borrow node in front of the create copy, and then it puts a terminate lifetime after the end. So in the middle here, we have this immutable reference to a string, which is the actual type that this node takes. And then we still have our copy string out. So these are in all ways basically identical, because again, the compiler is going to rewrite this to this, and this is the actual code that it compiles. And I mean, and part of the reason for that is, like, in order to type check this more, accurately, since this thing is expecting a reference in, it needs to be written in a form such that it's actually getting a reference in. Well, in order to do that, so effectively what that's saying is that if we have a node like this that really takes an immutable reference, we are allowed to wire to it either an immutable reference of that type or a mutable reference of that type, which we can coerce to an immutable reference, or just that type, which we can temporarily create an immutable borrow of, and then terminate or give back that borrow immediately after, because those things are all equivalent. In order for the type inference algorithm to be able to do that, it has to know for nodes like this that there may, in fact, for terminals of a node like this, there may be not one but two different variables. And it calls these, so it calls these the facade variable and the true variable. The facade variable is the outer variable that the connected wire sees, that basically anything from outside the node will see. And then the true variable is a variable of the actual type that the node is expected to consume. And it has to leave these two variables in place up until the point where it can prove that these two variables aren't both needed because they're the same type. So in this bottom case, like here, since we've actually written an immutable borrow before create copy, and we created an immutable reference, which is literally the type that this thing expects. Once it has done enough type inference to determine that this is compatible with what this expects, it will go ahead and merge those two variables together and say, okay, there's actually just one variable on this wire and on the terminal for this node, and its type is immutable reference. Whereas in this case, it does the type propagation, or does the type inference and says, okay, this outer variable is string, but the inner variable is still a mutable reference to string, and those aren't the same, so we have to keep these variables distinct up until we can automatically insert code that turns the one variable into the other, which in this case is inserting the immutable borrow. So doing that kind of two-step, okay, let's treat these things as potentially separate until we have enough information to prove that they are or are not separate. What that means is that our rules, our type inference rules, are no longer actually bidirectional, and it matters which order they get applied in. So for that reason, type inference, while normally or formally it should be able to be applied, you should be able to merge the variables or unify the variables in any order. In practice, in rebar, we still have to unify variables in Dataflow, like input to output order, so that we're able to do things like preserving these true and facade variables correctly. Okay, I think I have basically said everything I wanted to say about type inference, and this is a really fascinating topic of compilers for me. Like the fact that this is able to work. The fact that you're basically able to solve essentially a logic puzzle within the compiler, and then at the end you get a complete description of what all the types of your variables are, and the fact that means that they're able to nodes that are distant from each other are able to communicate in terms of what types they need is really pretty interesting to me. So this part of the compiler was a lot of fun to implement, and it's still kind of like interesting to come up with like solutions to problems that use this. So I hope if you're seeing this that this was interesting to you, and with that I will sign off. Thanks for watching.